to lots of pollutants or changes in water quality. Okay, sorry, I skimmed over that when I was editing and didn't get the milk. But they're sensitive to all pollutants and changes in water quality, and they're very predictable. Um, and so we can say, okay, if this pollution increases, we're going to see a drop in this species, and that happens. So they're a very reliable indicator of water conditions. And here's just a bit of a key. So when we have very intolerant species or families which are very intolerant to pollution, it means that the water quality will be fantastic if we see these. And in fact, even once our wetland filled up just the other day with nice fresh water, we saw an increase, a huge increase in stonefly nymphs, riffle beetles. We saw some fantastic intolerant species, which meant our water quality in our wetland was very good. Um, and we don't get those when it's dry and it's been stagnant for a while. We only get those species with an increase in rainfall. You can look through some of these other species, and as you go down, in almost all water, you're going to find bloodworms. You're going to find aquatic worms, and you might find things like planaria, um, which can tolerate quite a lot of pollution. So sampling macroinvertebrates, it complements chemical sampling. So yes, we can go and we can test for pH, and yes, we can go and test for nitrites and nitrates. But what this does is it tells us how these pollutants are affecting the environment. It actually tells us exactly how it's affecting the environment. Not only this, but they're also useful in detecting intermittent pollution. So pollutions which occurred once and then haven't occurred for a while, they might occur again. So we might test the water and it seems normal, but there might have been a dramatic increase in, say, temperature or pH or nutrient load maybe a month ago, and now that's settled down and we don't detect it, but what happened is still noticeable in the food chain. So let's say there was a real huge flush of really cold water, and all the macroinvertebrates died apart from the most tolerant ones. Now we can detect that change, even though the water might be back to a normal temperature. Um, and that's some physiochemical indicators, so pH, temperature, soluble phosphates. They're all physical and chemical, and they're not detected unless they're measured at the specific moment that they happen, except for we can look at now, hey, these species should occur here, but they're not. That means there must have been a change that happened over time. Cool. You need to check that the macroinvertebrates are correct for your location. So stonefly nymph, as I said, they're really good indicator of high water quality. However, they only occur in cool regions. They don't tolerate an increase in temperature. You're not going to find stonefly nymphs around in summer as much, and you're not going to find them around in maybe Queensland or the Northern Territory. But for where we live, they're um, a fantastic intolerant species to use for as a biological indicator. Um, so you can use both high tolerant and low tolerant species, as I kind of talked about with the ibis a little bit. So the EPA has a key of families of macroinvertebrates that they use, and some of them are tolerant, some of them are intolerant. And here's just a few, I guess, indicator species and what they tell us. So if we have an increase in population of bloodworms, then we're going to have a more dissolved oxygen levels. And if we have caddisflies which increase, then sediment levels may have increased. If we have stonefly nymphs decrease, then maybe water temperature has increased. So there's just a whole range of things there that we can work through. And we looked at lichen a little bit the other day. That's a pretty simple look at it. We looked at it in a little bit more detail. So that's what we're looking at for water and for aquatic systems. when we're talking about land ecosystems, there's a few other things we can think about. One that we already looked at Cape Conarin was the presence of introduced species. So introduced species affect natural food chains as well as habitat structure, and they can contribute to extinctions and predation and habitat alterations. They can outcompete native species. If there's no introduced species, then that indicates a healthy ecosystem, and vice versa. If there's lots of introduced species, then chances are your natural ecosystem is not faring too well. So in Cape Conarin, we were looking at the presence of deer and foxes, and that indicated, hey, maybe this isn't super healthy compared to the unburnt area, which had no present. We didn't detect any introduced species or very few, and so we can say, okay, this might be a healthier system. Not just animals, though. We're also talking about gorse, which is pictured, blackberry, serrated tussock, a wide range of plants as well, which can infest systems, not only on land, but also through waterways as well. But yeah, introduced species are a really good a really good biological indicator to an ecosystem, to the health of an ecosystem. All right, so a few key terms to finish us off here. The first one is biomarkers. So this is using indicators to kind of tell us a bit more about our system. Now, biomarkers are specific species that have a low threshold for a particular contaminant. So they mark, they're biological markers that that contaminant is there. Okay, so biomarkers, sorry, it's not there. So if the biomarker is present, then we know that contaminant is absent, because they have such a low threshold that if there was any bit of that contaminant, then those species wouldn't exist. So at low levels of contamination, they might show signs of abnormal growth, or then even at higher levels, they can die. And so we can assess really quickly and clearly if a contaminant exists using biomarkers. It means we need sensitive organisms that live in the ecosystem we're investigating, and the aim of biomarkers is to detect really low levels of contamination, okay, to detect the contamination as soon as it happens. Another technique is using bioassays. So this involves exposing an indicator organism to test how it responds. And we kind of talked about this when we were doing bioaccumulation, because that's where this is used. It's most commonly used to assess heavy metal concentration, and that's the lethal dose 50 tests, where we test a population of an organism or individuals of an organism to see how they respond to a particular contaminant. So then we can go into the field and we can see those effects and how they're working. So bioassays are tests and toxicity tests that we do to measure effects such as mortality and life history changes. So we test these things in a lab to see how these organisms react. And usually, at the moment, it's used for bioaccumulation, or that's where it's used at the moment a lot. So bioassays is testing individuals and organisms within labs to see their responses, and biomarkers are finding those really sensitive species and using them to detect even the slightest change in contamination.